And let's hope that that's the last one. It would be nice if we could get through the 68, 95, 99.7 rule in a day. Okay, darn it. I didn't start the thing. Where is this? Okay, let's try again. Here we go. Okay. Since we were talking about it, let's change the data here. Instead of talking about instead of doing SAT scores, let's talk about baby birth weights. So average baby birth weight is about 7.2 pounds. So at birth, most babies, the average is 7.2 pounds. That means right down here, we have 7.2 pounds as what an average baby is born, right? You can, by the way, you can go double check me on these stats, but 7.2 is pretty close, okay? The standard deviation for that is approximately like 1.4-ish pounds. Or 1.4, yeah, 1.4 pounds. So average is 7.2. The standard deviation here is 1.4. So how many of you guys know how much you weighed at birth? Awesome. So we can do a bit of a test here, and you can find out just how abnormal you are. And I'll tell you how abnormal my kids were. Because if we know the mean, we know that the middle point right here, the spot right in the center of the big hump on the normal model, is 7.2. Now, each of these little things is one standard deviation to the right or to the left, which means if you take that standard deviation value and add it to the mean, we can find out where one standard deviation above the mean is. So that's about 8.6. And then 2 standard deviations above the mean is about 10 pounds. And then 3 standard deviations above the mean is about 11.4 pounds. And then if we go this direction, we've got 5.8 as 1 standard deviation below the mean. We've got 4.4 as 2 standard deviations below the mean. And we have 3.0 as 3 standard deviations. Okay. Very small baby, but it happens, right? Premature birth happen all the time. In fact, one of my former students just had a preemie last year. How big was he? He was like, I want to say he was like 4 pounds. This wasn't my kid. This was a former student. But yeah, he was born 3 months old, 3 months early. He was like 4 pounds. He had to spend the first month of his life in the hospital. It's ridiculously hard, both on the family and the baby. But it unfortunately happens, right? And that's this group of babies down here, right? And then these are just giant kids who yeah. So Escher, my youngest child, is right about there. My youngest child was 10.5 pounds. So he was right about there. My other babies were about here and here, because they were 9'11" and 9'7". So those were my kids. I was 7-ish. I was pretty average, but I was a C-section baby, and it was like, here's your due date, come in for your C-section at this time. So these kids were all, let's see. Baxter was 8 days late, and he was actually the smallest. He was 3 days late, and Escher was 4 days late. According to the due dates, they're always. So you can kind of see where you fall. If you know your personal birth weight, you can see where you fall somewhere in the grand scheme of the data here. Because birth weights do tend to be fairly unimodal and symmetric, so we can model it with the normal model. Now remember, this isn't right. This is just a model, right? All models are wrong. It's just that some of them are useful, right? This one can be useful because we can kind of see where things fall. Brittany? No, this is for all babies. Probably a little bit smaller, yeah. But I think in terms of, as far as I know, if you're looking at the population of all babies, including twins and triplets and stuff, this is still them. Because look, even 6.5, that's not terribly uncommon. I mean, you're a little bit below the mean, but you're within one standard deviation. That's still a common birth weight. So. I don't know how common. I don't know if I've ever read any data about how common twins are. I think it really depends on your family. Twins tend to run in the family. My dad has 7 brothers and sisters, 3 sets of twins. Yeah, 3 sets of twins. Your dad, my dad and my Aunt Katie are the only 2 that don't have a twin. Yeah, and within those families, there's 2 sets of twins and a set of triplets. So, yeah, it's too many kids. Too many kids. But yeah, but they're not. I didn't have any of them at the same time, which really makes a difference because you get a bit of a break. We were honestly scared to have a 3rd kid because we were like, if we have a 3rd kid and it's like triplets, I don't even know what I would be doing right now. Yeah, exactly. Like I barely sleep as it is. So, any of you guys surprised by how abnormal you are? How many of you guys are within that you know of are within 1 standard deviation? Within 2 standard deviations? Anybody out there by the 3 standard deviation? Big kid, and 11.2? Dang. Were you late or on time? Or, my mom was 11.36 hours. The largest weight of a baby ever born. Jesus Christ. That's like how many standard deviations above the mean is that? That's like 6 or 7 standard deviations above the mean. So incredibly rare. Ridiculously rare. I was like 12. But I guess it is. Is that the same baby that's like 2 years old and smoking cigarettes? Have you guys seen that story? It's like a Filipino baby. It's like 2 years old and he's addicted to cigarettes. It's actually a really sad story. But he's a super kid is like a super chunky kid. Are you guys looking at pictures of him? And you're all going, ooh, that's not good. All right. So anyway, we can, based on looking at this kind of graph, we can say a lot about the percents, right? I can say that the middle 68% of babies born are between 5.8 and 8.6 pounds, right? Because that's 1 standard deviation below the mean. I can say that the top 5%, actually I could say, no, not the top 5%, the top 2.5% of babies are above 10 pounds. Because you can also break this down in between. Like we know that from here to here, we know that from here to here is 68 pounds, or not 68 pounds, 68%. But if this in here is 68%, then that means that this area out here, well, let's see here. Let's do some math. If this is 68%, how much is this section plus this section? 100 minus 68, which is 32. So if that's 68, these outsides are 32. So what's this area over here? Remember, this is symmetric. It's perfectly symmetric. So if both of these are 32, what's this over here? 16. You went the other way, right? If that's 68%, then 100 minus 68 is the outside bits here, and that means that half of it is 16%. If this is 95%, what is the two outsides here? Well, 2.5 each, right? Yeah. So if this middle part is 95%, then this bit right here is 2.5%. We could even go so far as to break down each individual section. If this bit is 68%, then this bit right here between 0 and 1 standard deviation is going to be half of that. So that's 34%. And 34 plus 16 makes 50, so that makes sense because that's that whole side. So the empirical rule, that's what this is also called, the empirical rule, 68, 95, 99.7 rule, it breaks down the normal model by percentages. And so we can see just what percent we need in order to accomplish things. Hi, Lizzie. Notice I made her walk all the way up here. Yeah. And then I'm going to walk halfway. Bye, Lizzie. It's fun to fuck with you. So we can break it down by percents, right? We can break down each individual section. We can add up sections. And it allows us to sort of quantify that data a little bit. So I'm going to have you guys draw your own model. You can do this. I don't think I left room on the paper. Did I leave room on the paper? What's the example that I said? Is that the same one? The Dutchman example? Yeah. So why don't you guys go ahead and do the Dutchman example? I want you to draw the normal model. Draw a little normal model, and I want you to label where each of the standard deviations are, like we just did on the previous slide. I'll even go back to that previous slide. I want you to draw out that model, and I want you to label what all of the standard deviations are. I usually try to print notes so that there's notes on one side and a blank piece of paper on the other side, so that you can write these things out so you have enough space. I'm going to pause the video so that you don't have to watch it. So like awkward silence. You do the very same as you act like a smartass. Yeah.
No, but he frustrates me sometimes, and I'll ask him a question, and he's like, yeah. And then he walks away. I'm like, that's just it. I asked the question.
Are you a boy or a girl?
Oh gosh, this is frozen. I'm like, why is it doing this again?
Are you a boy or a girl?
So yes. I'd be like, so it's like this is this, or is it like this is this?
What is happening? Are we recording right now?
But then he walks away. What was that?
So let's do this thing. I'm going to draw the model. What was the mean? 184. And the standard deviation is 8, right? So this is 192, 200, 208. And then over this way, oh my, 176, 168, and 160. So we can use this information to answer all the questions about the Dutchman. So the first question is what? So which percentage is over 200 centimeters tall? First thing that you guys need to do is be able to recognize what part of the graph we're talking about. Okay? If it's over 200 meters tall, we are talking about this little section right there. And once we understand what section we're looking for, we're going to say, well, if that's the section I know, let's start kind of like process of elimination to find out what percent that is. Because we know that this bit from here to here is 95%. So if that's 95% and the whole thing is 100%, that's 95. That means this plus this is 5%, which means that highlighted little section is half that. And so the first one here is 2.5%. Because we're taking just that little sliver. This is 95, so this is 5, so this is 2.5. What's the next one?
168 over.
Over 168. So again, looking for this section of the graph that we're talking about. Everything over 168 is from here over. So what do we know about that section? I know that from here to here is 95%. I know that from the previous problem that this section is 2.5%. So 95 plus 2.5, number 2 is 97.5%. What's number 3? 176 and 168. So we're talking about that section right there. All right, what do we know? So we know that from here to here is 95%. Does that help? Kind of. We know that from here over is 97.5%. Then we just have to take out from here over. That's one way we can do this, right? You can take the big amount from here to here and subtract the small amount from here to here, and that would give it to you. Kelsey? Say that again. Okay, subtracting 68 from 95 gives you this section, and then divided by 2, that'll work. So what do we get when we do that? 13.5? 95 minus 68 is, 95 minus 8 is 87, minus 60 is 27, divided by 2, 13.5. Looks like 13.5. Okay? So yeah, notice that there's more than one approach that you can take on this. 95 minus 68 divided by 2 will give you that. This whole section that we found, the 97.5, minus this section, and then would also give you the same thing. You could take the whole 100%, subtract 68, and then subtract 2.5 and 2.5. I mean, you could go about this many ways. Go ahead. 16. Oh, from here to here?
Yeah.
Yes, you could. If this is 68, that means that this is 32 and this is 16 minus 0.5, 2.5 gives you 13.5. That also works, right? Lots of approaches. It's about knowing where your 68, 95, and 99.7 rule is and what you're looking for, and then just subtracting things away. Number 4. Sorry, say that again. 18. Wait, say it again. So 184 to 208. So we're looking for that section right there. Again, many approaches. You can do this a lot of ways. Here's the way that I did this one personally. From here, the halfway point over is 50%. So that just means I need to find this little section out here. Well, that is 3 standard deviations. This is 99.7. So this is 0.3, which means this is 0.15. So 50 minus 0.15 is 49 point something? 49.85? Start with a big amount and then start subtracting the smaller things that are within it. What was number 5? 176 to 192? Did I really make that one the last one? Because 176 to 192 is super easy. I hope we can get that one. 68%. What's that? Over 208? Yeah, and technically speaking, we did over 208 already too, right? Because I found it when I did this one beforehand. So over 2.8, well, we already know that that's 0.15%. Yes. Yeah. 49 should be 49. Because it's the full 50% minus just the 0.15 that is past this. Because that's past 3 standard deviations. So okay, gotcha. Questions, comments, concerns? Okay, so 68, 95, 99.7 rule, these ones that we just did, they work out really nicely because all of the numbers we asked for fell exactly on a standard deviation. However, that's not always going to be true, right? Obviously, there's going to be Dutchmen that are 186 centimeters tall, right? And to find that out, we can't just take the distance between here and here and knock off a certain percent. Because look, this change as you go down is not linear, right? If it were linear, you could draw a straight line and the areas would be the same, but it's not. This section right here is not linear, which means that when you're in between, you have to follow the area of the model, and you can't just use some like linear guess, which is annoying because finding the integral of a normal model is very difficult. But the good news is that instead of trying to find out the exact standard deviation and trying to do it that way, we can use another tool that we've already learned, and that's the z-score. Because remember, the z-score is the number of standard deviations above or below the mean. And so, if we found a z-score of 1.5, a z-score of 1.5 is going to be directly in between those two values. But we then have to find what the area of the curve is under that. And the good news is that there's a bunch of mathematicians who have done that for us already. They've created a normal model, and they even have giant tables and calculations that will do every z-score for you. Okay? We just have to be able to learn how to access it. And that's the point of tomorrow's lesson. Is now that we have an understanding of what the normal model looks like and those percentiles within, and that 68, 95, 99.7 rule, tomorrow's going to be all about finding those exact percentages for any z-score. Okay? And that's what we'll do tomorrow.